Picture this. May 6th, 1937. The colossal airship Hindenburg, the pride of Germany, glides majestically toward its landing mast in Lakehurst, New Jersey. It's the pinnacle of air travel, a flying luxury hotel. But within moments, this symbol of modern engineering would become a horrifying spectacle of fire and destruction. For decades, the story we were told was simple. The highly flammable hydrogen gas that kept the Zeppelin afloat must have ignited. But how? What was the spark that lit the fuse on one of history's most infamous disasters? Today, we're diving deep into the most widely accepted theory, the incredible power of static electricity. The Hindenburg was late. A line of thunderstorms had forced it to circle for hours, waiting for a safe window to land. This delay was crucial, as the massive airship flew through the humid, electrically charged air. Its fabric skin was accumulating a massive static charge, just like you do when you shuffle your feet across a carpet on a dry day. The ship's frame was made of duralumin, a conductive metal, but its outer skin was made of cotton fabric, coated with a special paint called dope. This dope was meant to protect the fabric and reflect sunlight, but it had an unintended fatal flaw. It was not very conductive. The static charge built up on the skin, but it couldn't easily flow to the metal frame to be grounded. The Hindenburg had essentially become a giant flying capacitor, storing a huge electrical potential. As the ground crew prepared for landing, they dropped the mooring lines. These lines were wet from the rain and became a perfect pathway to the ground. When the ropes touched the earth, they began to ground the Hindenburg's metal frame. Here's where the disaster begins to unfold. The metal frame started to lose its electrical charge to the ground, but the fabric skin, which was electrically isolated from the frame, held on to its massive static charge. This created a huge difference in electrical potential between the skin and the internal metal skeleton. A spark was now inevitable. All it needed was a place to jump. Eyewitnesses reported seeing a faint blue glow on the top of the airship, just before the flames erupted. This glow is often described as St. Elmo's fire, a weather phenomenon where plasma is created by a massive electrical charge. This was the visual evidence of the immense static buildup. The breaking point came when a spark, energized by this huge voltage difference, leaped from the charged outer skin to the grounded metal frame. But what did it ignite? Hydrogen. Now, it's true the Hindenburg was filled with 7 million cubic feet of hydrogen. But this gas was safely contained within 16 large gas bags, or cells, inside the ship's structure. For the spark to ignite the hydrogen, there needed to be a leak. Investigators believe that a sharp turn or a broken bracing wire during the turbulent flight might have torn one of the aft gas cells. This would have allowed hydrogen to leak out and mix with the oxygen in the air, creating a highly explosive mixture right in the path of that inevitable static spark. The spark jumped, the hydrogen-air mixture ignited, and the fire spread with terrifying speed from one gas cell to the next. The chain reaction was catastrophic. The initial flame appeared near the tail of the airship, exactly where a hydrogen leak combined with a static discharge would most likely occur. Within 34 seconds, the entire structure was engulfed in flames and crashed to the ground. The famous radio broadcast by Herbert Morrison, with his emotional cry of "Oh, the humanity," captured the shock and horror of the world. He was describing the scene as a simple hydrogen fire, but the science behind it was far more complex. So it wasn't just one single thing. It was a perfect storm of unfortunate events. The stormy weather, the electrically charged atmosphere, the non-conductive skin of the airship, a potential hydrogen leak from a sharp maneuver. It's the final act of dropping the grounding ropes. All these factors combined to create the conditions for a massive static discharge. This static spark theory is now the most widely accepted explanation among airship experts and historians. It paints a more nuanced picture than simply blaming the hydrogen. The hydrogen was the fuel, but static electricity was the match. Other theories have been proposed over the years. One popular one was the incendiary paint theory, which suggested the paint on the fabric skin was itself highly flammable, like a solid rocket fuel. While tests showed the paint could burn, it couldn't account for the incredible speed and ferocity of the fire that destroyed the Hindenburg. The fire spread much faster than the paint could have burned on its own, pointing back to a massive hydrogen-fueled inferno. Sabotage was also considered initially, but no evidence was ever found to support it. The evidence, from eyewitness accounts of the blue glow to the location of the initial fire, all points back to that fatal spark. The Hindenburg disaster effectively ended the golden age of passenger airships. The terrifying images were seared into the public consciousness, making it impossible to convince people that flying in a hydrogen-filled balloon was safe. It's a powerful reminder of how a series of small, seemingly unrelated factors can converge to create a catastrophe. The legacy of the Hindenburg is a lesson in engineering, atmospheric physics, and the unforgiving power of nature. It stands as a testament to the fact that even the most advanced technology of an era can be brought down by one of the oldest forces we know: a simple spark of static electricity. Thanks so much for watching. If you find these deep dives into historical mysteries as fascinating as I do, be sure to hit that subscribe button and ring the bell so you never miss another history. Until next time, stay curious.